As I begin to speak about this, and I'm ready to transition to my chart, I just want to say that I found that understanding the human element is critical in designing systems where, especially astronauts go. So I'm hoping that everybody can see my presentation charts. Yes.
Yes, we can.
Okay, great. All right. So basically the many paths of human interfacing design for future space missions, and the reason for the Myriad path is because there's many things that are involved associated with developing human interfaces for future space missions. I'm sure you have read story after story of failures of airplane that have crashed because of human error. Um, Pilot plants, manufacturing plants, chemical plants that have exploded because of human error. Ships, not too recent, was a U.S. Navy ship called the USS McCain that crashed into another ship and killed, I think it was 5 sailors. That was human error, and so NASA takes human error and human design of systems very important. And so my presentation today is going to be talking about developing human systems or human interfaces specifically for space applications, but not to say that it's not applicable for other industries as well. We are very rigorous in designing systems for space missions. And so I'm going to be talking about future space missions, kind of give you set the stage, if you will, about the challenges NASA has in going to deep space and why we have to consider the human interface and factors of in human machine interface. I'll be discussing at length the roadmap to a robust human machine interface design, HMI. I might be saying that quite a bit, but it's basically human machine interface design, and then wrap up. Right. So next up is future space missions. Right now, space station is orbiting around the Earth at about 260 nautical miles, and we got something like 14 different nations that are participating in International Space Station. A lot of these activities is what NASA calls Earth dependent operations, which means that these operations are happening very close to Earth, and astronauts depend a lot on Earth, especially Mission Control Center, to help them out operating the space station. The space station is a very complex system. It has over 350,000 sensors, over 100 computer systems that have to be monitored 24 hours a day, 7 days a week throughout the year. And no 3 astronauts, or 4 astronauts can do that. You got to have people on Earth. And you see here a picture of not just let's see if I can turn on my laser pen. Let's see. Not just the Mission Control Center, but we also have in the back room of Mission Control Center in Houston, Texas, we have what we call the Mission Evaluation Room, which is comprised of many engineers that understand the systems on station very well. In addition to that, we also have the Russians that have a control station in Moscow that also monitor the systems. And this is all related to space station because of the complexity of it. So let's fast forward to the future, and this is notional, that we'll have a orbiting, we call it orbiting gateway on the moon. As let's call it the Moon Space Station, for the lack of a better term. And that orbiting space station is going to take about 1.2 seconds to communicate to the Earth because of the distance and communication, the physics of communications. And so we're still going to have mission control because we had that in the Apollo space program. Even though it was going to the moon, they could still communicate in a timely fashion with mission control. But as we start going to the moon, rather to Mars, it's going to get really difficult because it takes about 20 minutes for a transmission of a signal to go from Earth to the Mars and Mars back to the Earth. And so we're going to have to depend more on onboard mission control, artificial intelligence. And there's challenges with that too as well because of the nature of the radiation environment and the electronics susceptibility to radiation effects. And so right now, we are going from a crew mission control dependent operations where we depend on mission control to crew machine dependency because we're so far away that the crew is going to have to depend on their knowledge, their skill, their problem solving, their creativity, and the machines that are going to deep space to help them solve complex problems that maybe we didn't train for because we can't anticipate everything that's going to be going on in one of these deep space missions. Everything is new to us. We've been to the moon, but only for a total of something like 3.2 days. If you add up all the Apollo landing of humans, we had 12 astronauts that walked on the moon. Then if adding all that up, it's only about 3 days, which is very small compared to what we're trying to do now with the Autonomous Space Program, which is basically learn to live on another planet for a long period of time. Take that knowledge, that understanding, and development of these systems, so that way we can go to Mars, and then Mars is going to be the proving, not necessarily the proving ground, but it's going to be the verification, validation that humans can live independently on another planet for a long period of time. Now, that's a major challenge. Along the way, we have major complex systems that we're going to be developing, and those complex systems are going to require human interfaces. Just simply because we're going to have humans in there. These human interfaces are going to have to be very adaptive, very robust in handling all the different situations that can occur on a deep space mission. And so some of the human-machine interface applications that you see here is just not the spacecraft controlling the spacecraft, but we may have a pressurized rover on the moon or Mars, service habitats, where astronauts will live for a long period of time. And then you got the astronaut extra vehicle activity with a robot in a collaborative fashion doing a task on another planet. And then, the types of displays are basically like displays and controls. As you see here, this is the robotics workstation on International Space Station. And then you have wearable technology that human in the crew is wearing these control systems and monitoring systems that are wireless, used to not just monitor the crew in terms of health, but also provide controls. And so, how do we do that in the presence of issues associated with deep space missions? So next up is where I'm going to spend a little bit of time about factors in human-machine interface design. And I first want to talk about the human element and kind of set the stage of many things that were not taught to me in school when I was an undergrad in engineering and even in my master's in systems engineering. But wanted to share with you that I learned along the way over the many years that I've been involved with NASA. And so I first want to talk about the human-machine capabilities. And NASA's findings on this occurred many years ago in executing tasks, and it still holds true today. Artificial intelligence is closing the gap, and I put an asterisk in some of the areas. But for the human, we're very creative. Okay, There's no question about that. We can take a bunch of things that are they don't look related and build things. I can tell you that from my personal background. When I grew up, where I grew up, there was a junkyard that friends of mine and I used to take stuff and build things, and so humans are very creative. Uh, Rapid retraining, we can adapt very quickly to training. We can function under overload conditions. We can still function to a certain extent when too much is being put on us. We'll be able to handle it in an adaptive fashion. We reason inductively, from a specific to a broad. We try to look at all possibilities, and that's actually good when we're designing systems. We evaluate the risk and unexpected events. We use equipment beyond its specific limits. Sometimes again, because of the creativity of the human, we can take a machine that we think we understand quite well and use it for actually other applications, or basically modify things to make it work better. And then sense certain stimuli that machines cannot. I mean, we can sense things like, for example, is it getting too hot? It feels warmer. I had an opportunity to talk to one astronaut on a space shuttle mission, and he said he could smell something that didn't smell very well, but some of the machines did not pick that up right away. So humans are very good at some of these things. Machines, well, computer systems, they're very precise. Robotic systems can repeat a motion thousands of times and not get tired. And machines don't complain that they're working too hard. Quicker response to stimuli. What are the reasons why when we launch, the astronauts are not controlling the vehicle? Is because things are happening so fast that the humans' capabilities and limitations are too slow to handle changes in the launch of a rocket. That's one thing Werner von Braun in the Apollo space program had basically was very adamant about, was that he wanted computers to control the launch of a vehicle and not humans. Store and recall large amounts of data. We can do that. The astronaut, or rather, computers can do that quite well. I mean, they can store millions, billions, and of data and retrieve it at any time. Reason deductively, it's the nature of computers, function in a wider range of stress conditions. That's why things like oil and gas industry are looking at robotics for going into some of the areas that are more hazardous for humans to go into. And same thing for astronauts going into deep space. Every time an astronaut does an extra vehicle activity in the spacesuit, it's a hazardous situation. NASA does not like for their astronauts to go out and do an extra vehicle activity because there are many hazards. One can be a meteorite strike on the spacesuit that can puncture a hole and basically, really get rid of all the air that they have inside their spacesuit, and obviously cause major problems. Machines can be much stronger. We have a robot called Robonaut, and he can hold 20 pounds at arm's length for a indefinite period of time. Compared to a human, they can only hold 20 pounds out for a specific period of time, and then all of a sudden their muscles are starting to ache, and they can no longer hold it. Machines can't sense stimuli that humans cannot. I mean, they can sense, like, for example, radiation. We humans are not geared to sense radiation, but, like, for example, the Geiger counter, right, is a machine that can sense radiation. So if you're not familiar with a Geiger counter, it basically it does click sounds, audio click sounds, and the click sounds indicate the presence of radiation. How fast that clicking is happening tells you how bad the clicking, or rather how bad the radiation is. So let's talk about the physiological and psychological challenges in deep space, and there are many. So we have, first of all, altered gravity. Okay, physiological changes can happen with the changing gravity. Balance disorders, fluid shifts. Okay, so fluid shifts, like for example, I don't know if you notice, but if you ever see pictures of astronauts that've been on space station for a long period of time, their face looks very bloated, very big, and that's because the sinuses do not drain in a microgravity environment. Muscular atrophy, in other words, your body kind of grows a little bit, but you also have bone loss because there is no gravity pulling on the body. The body says, "Hey, I don't have to compensate for the gravity environment, so I'm going to stop producing calcium." And so your bones become brittle. So you got to develop exercises, to keep them physiologically healthy, if you will. And then space radiation. This is the biggie. It's one of the major challenges of human spaceflight going into deep space is the radiation environment. On space station is not so bad because the space station is inside the Earth's magnetic field. And of course, the Earth's magnetic field, as you can see here, basically protects against galactic radiation and solar radiation that bombards the Earth. And so it's going to be a major challenge once you get away from the Earth's magnetic field is to deal with that. Isolation and confinement. This is more of a behavioral aspect of isolation. Sensory deprivation. In other words, we no longer sense that we're on Earth, we're on somewhere else. Sleep disorders. As we get further away from the sun, the amount of the intensity of the sun, the reduction in interaction with the body goes down, and so it basically upsets how we sleep and things like that. Isolation is going to be a biggie. We've done studies about 1 year isolation studies with astronauts and even on space station, but we still don't know what's going to happen to the astronaut when they see Earth very small and they know they cannot go home. I had an opportunity to talk to a Russian scientist many years ago, and a Russian scientist told me that some of the Siberian studies they did in isolation studies, one particular person commented that the only reason he survived or was able to last over a year in isolation was because he knew he was on Earth, and one day that door was going to open and he was going to get out and see his family. That was the motivation for him. Hostile environment, vehicle design. We got to design a vehicle to deal with a hostile environment, like for example, radiation effects, carbon dioxide levels, toxic levels. But we also got to deal with feeding the astronauts for a long period of time, especially when we go to the moon. But habitat design is obviously a critical factor because it's very difficult for astronauts to work and live in a very confined environment. Think about yourself. If you're trying to work in a room that's only maybe 1 meter by 1 meter by 1 meter in diameter, and you're in there trying to operate a computer system, it becomes very, very objectionable in operating a system in that kind of environment. And then if it starts getting very hot, so now you have to deal with being hot, deal with it very, very small quarters, confined quarters, and you might be depressed or not feel well. So now you got many factors affecting the operation of the system. And certainly medical situations, being away from, so far away from Earth, appendicitis or heart attack. What kind of remedies do we have? Well, I can tell you that all the medical systems that we have here on Earth are not going to be able to operate in the deep space environment. We're going to have to, what we call radiation harden the electronics to operate in a deep space environment. And so,
Excuse me, Mr.
one of the,
Salazar.
go ahead.
Yes, very sorry to disturb you. So there's a little request from the organizing team asking whether you can switch on your video camera.
I'm sorry, can you repeat that?
Yes, there's a small request from the organizing team. They're asking whether if it is possible for you to switch on your video camera.
Oh, yeah, stand by. All right, do you see that?
Yes, thank you, Mrs. Khalza.
All right. Okay, sure. Um, I'm going to go back to presentation mode and start picking up on situational awareness because this is now starting to get into the human interface factors affecting human interface design. So here, a contributing factor in situational awareness, and so let me just say that situational awareness is basically understanding what's going on. And so, you first have spatial awareness. Okay, where am I? Am I up? Am I down? Am I sideways? Or which way am I? And then you look at the system awareness. So there's a cartoon there that says, there's the pilot and the co-pilot, and the pilot says, "Hey, the fuel light's on. Frank, we're going to die. We're all going to die. Wait. Oh, my mistake. That was the intercom light." And so misunderstanding of what the system is telling you can be a big thing. So, even though this is a cartoon, it's very realistic as to what can go on because if you misunderstand what status you're getting back from your system, you can press the wrong button thinking that this situation has happened when in fact it's not. So system awareness is important. Task awareness. What are you doing to complete the task? Is and also is it difficult? And demands of each task arrive interleaving. So sometimes you have multiple tasks going on that you have to deal with. And so how do you know which task to address first, second, third, and things of that sort? So this is situational awareness, and this is very critical when a human's controlling a machine, especially like, for example, an airplane, submarine, a um, a Navy ship, and even more so a spacecraft. So here's the importance of situational awareness, and this is taken from a lady by the name of Mika Ensley, and this is the model that she had developed. Let's see if I can get my laser pointer back on. And so she had developed this model here of the situational awareness. And so situational awareness is basically a function of perception. What's going around in my environment? Comprehension. Do I understand what's going on around my environment? And then reaction. Based on what I think I comprehend, what is my reaction? What do I need to do? Part of this is associated with your mental models of what you understand is the situation, what you understand is what the task is. Based on all this, you make a decision, right or wrong, hopefully right, is you make that decision. That decision results in action, results, and reach your goal. And so if you reach your goal, then your current state of the environment and the environment dynamics should be consistent with what you're trying to achieve. You got to keep in mind that humans only have one pair of eyes and hands, one mouth, and limited attention and cognitive resources. And that's the challenge. So situational awareness drives decision and performance, very critical in designing human machine interfaces. Again, this is one of the many different paths in designing a human machine interface for spacecraft applications and even other applications as well. And so working errors and failures can occur, and there's different areas where it can occur. So here's what we call what's called the HSI, Human Systems Integration System View. It's called Human Systems Integration is because it factors the human element into the design of a system. The hardware and the software and the environment was what I was taught in school. Build the best hardware, build the best software. Very little about the human. In reality, it's really about the human, the hardware, the software in the environment. Uh, I can tell you that you can have the best hardware, you can have the best software, works perfectly. You bring a human in there, and he or she doesn't understand how the system works. They hit the wrong button. There's a failure, and so the system as a whole fail, regardless of how well the hardware and software was designed. And so the two, actually, there's three areas associated where things can fail. One is here, the bathtub curve. You probably know this, especially folks studying engineering. And this bathtub curve is associated with mechanical and electrical systems. Is that you first have the burn-in phase, the early infant mortality, where things can fail early on because they're brand new. And so manufacturing processes and things of that sort probably did not do things, made things very well. And so things can fail. But after a while, after operating for many hours, you have a constant failure rate. And now you can predict when things can fail over a specific period of time until it gets to the wear out phase where things start to wear out very quickly for electrical and more so for mechanical systems. Now, contrast that with software systems. Software systems don't have moving parts or electronic parts. Okay, it's code. And how do you treat code in terms of failure rate? You treat code by the number of what we call uh, lines of code. And so if you have a large number of lines of code when you first produce your first software, you're going to have a high failure rate because you didn't get all the errors out. But as you continue using the software and evaluating it, the error rate goes down till you get to a minimal point where the failure rate is at a minimal known rate. But then, if you're going to upgrade the software, what happens? You're going to have errors again, and then you got to reduce those. And then you upgrade it again, same thing over and over again. That's why you see the soft waveform until you stop uh, upgrading the software and you start having just a constant failure rate. Errors and mistakes for the human are different. So I want to show you this diagram, and over here to the left-hand side is something from a gentleman by the name of Jim Reason in 1990 developed the Swiss cheese model of human error and hazard mitigation. And so basically what he developed was a model of why we have accidents. And it's all related to many different factors. It's just not one factor that causes a failure of a system. And so what you see here are barriers. So barriers are things that basically are part of development of the systems that you're trying to prevent errors from occurring. For example, you're trying to develop the best requirements, and you're trying to develop the best design, hardware and software. You're trying to do safety reviews, training, maintenance, and then obviously you want to have a very high performing crew. But we're human, and we're not 100%. We're fallible for making errors, for making mistakes. Swiss cheese, and this is my circular piece because things are rotating over a given period of time. That things can line up where an accident occurred. What you see here is, for example, one hazard was deflected as safety because safety caught it. There was a safety engineer that said, "Whoa, this this design is wrong. You need to correct this." Or during training, they found out that this was not a right sequence of procedures for executing a command. And so they were able to identify a erroneous commanding of the system. But then there's that case, that one day in a thousand, where things just line up. These holes represent imperfections in each one of these barriers. And it's just a bad day where things line up and an accident occurred. There was an accident in India, maybe it was about 20 years ago, where a plant blew up and killed thousands of people. I was reading the case study of that, and I think they had something like 19 different things, pieces of cheese, if you will, that lined up for the accident to occur. So it's just something to keep in mind. On the right hand side is a uh, basically a diagram of the kinds of errors that can happen with a human. Unsafe acts. So first of all, there are the unintended actions. And so you have things like a slip, okay? Uh, I know the system, but I forgot to do this step. Or, I know how this thing works, but I did step three instead of step two first, So you understand the system, but you have slips and then lapse, you forget. I tend to forget. And as I get older, I start forgetting more and more, but you forget things that was taught to you on how to operate the system. These are unintended actions. You know, but you make mistakes. And then there's the intended actions where this system is new, but you're going to make a mistake because you applied a rule that does not work in this situation. Again, it goes back to your mental models of how you think things should work, and maybe the system is not obvious how it should work, and so you tend to make mistakes. This one down here, for the most part, I have to say, is not a big issue for NASA. We don't do violations, acts of sabotage, and things of that sort. That's very uncommon, but I'm sure it can happen in the industry where you have a disgruntled employee that wants to destroy the plant or whatever. Um, Let me start talking about the roadmap to a robust human-machine interface design. And so the first thing that I show here is this is a systems engineering process that NASA uses. And so I'm going to kind of explain it briefly because I could spend 2 days on this. On the left-hand side is what we call the system design process. What happens here at the high level is what we define requirements, and we come up with some potential solutions to the problem that we're trying to address. On the right-hand side, we do the what we call the product realization. So here we built the part that we think is going to work. We integrate it, we test it, and we validate the system. In the middle, there's a lot of activity going on here, but this is important when you're developing systems, is the technical management process, like planning, requirements management, interface management. What am I interfacing to? What is the human going to interface to? Technical risks. What are my risks? What's the risk for the human using this system while they're doing extra vehicle activities? Um, Technical assessment. You're assessing your system all the time. You're assessing your design solutions all the time. And then obviously decision analysis. So before you do that, there's something called scoping, is to try to understand what the problem is. If you don't do this early on, you are going down what we call the wrong rabbit trail. In other words, you think you found a solution to the problem, but it turns out that you didn't. And so scoping has to do with understanding what's our needs, what's the problem, objectives, what's the mission we're trying to do, what constraints do I have in terms of cost, and in terms of schedule. What are my assumptions? Am I assuming that I'm going to be using this kind of technology? Am I assuming that this center is going to support us? Am I assuming that we're going to have to develop a new technology in order to accomplish our mission? And then who's responsible for what? This is important to avoid finger pointing later on. I thought you were responsible for this. No, I thought you were. Well, I thought he was going to do that. None of that. You have to identify who's going to be responsible for what. And so early on, you're doing the definition and the composition of a system. And then on the right-hand side, you're doing the integration and verification validation of a system. Verification basically says that we built this system right. Did we build it to the requirements? Did we build it to withstand the environment factors? Validation, did we build the right system? Did we build the system that solves the problem that the stakeholder or the customer wanted? That's kind of the big difference between those. Up here at the top is basically the life cycle of a project, starting from concept and technology development, preliminary design, final design and fabrication. The biggie there is critical design review, because that point is a formal review of the final system that's going to be developed for flight. And then the assembly integration, systems integration review, test readiness review, systems acceptance review, operational review requirements, flight readiness review. This is where you fly, you launch your system, and then you have operation of the system until you get ready to dispose of it because the end of life. Now, here's another aspect of it. It's at a very short level is the systems engineering process. It's developing requirements, which means you're maintaining requirements, changes to the requirements, controlling the requirements, verifying the requirements, validating the requirements. Along the way is the human systems integration aspect of it, both the technical and management process that includes the human. And so what you're seeing here is what we call the human-centered design as part of systems engineering. And so you, as part of systems engineering, like for example, technical planning, you're also planning the human element. Like for example, when do we test for for this system with the human, and who's going to be responsible for developing the procedures for the human test of the system, context of use and that and the environment is going to be used. This is related to concept of operations, how the system is going to be used, not just nominal but off nominal, and also the the tasks that are going to be needed. And then the design solutions. Okay, what solutions have we come up with? And then finally, evaluating the systems. I have another chart about this, but what we're trying to do with the human element, human systems integration, and systems engineering is we're trying to maximize system performance, reduce the costs, and reduce the risk. I can tell you that cost is a huge thing when you did the fact that it happened on space shuttle, it happened on space station. We were designing the system for meeting the requirements with very little attention to the human element, and it cost us a lot of money. All right, so here's another description of the activities going on with developing a human interface. You're developing the requirements, but along the way, you're developing the concept of operations, as I mentioned previously. You're developing the behavior of the solution. I'll say more about that later. And then you're also developing the physical solution. What parts do you need to implement this human interface? You're evaluating all of these options, and that's where you see these errors, very iterative. And then you do a technical assessment and decision analysis: is which system should we use? And so, in the end, you're proposing a design that takes you up to preliminary design review. This is the design we choose, and then if that's the design you choose, then you do further refinement of your design, which is called the detailed design, that takes you to critical design review. That's a major decision point for NASA. This is the system that we're going to spend a lot of money, a lot of time, a lot of people's effort to build, test, verify, and fly. This is the human-centered design that I mentioned on the left-hand side. This is again factoring the human element, always having the human in the loop. And on the right-hand side is more the integration, verification, and validation. You're building the system, your component, you're doing component verification and validation, and not just component, but system and subsystem. You're doing run for the record. Yeah, you're going to prove that your system meets the requirements, like human in the loop testing. You're validating, you're comparing against the system level requirement concept of operations. All along the way, you've got technical management processes that are overlooking all these activities to ensure that there are no issues in terms of risk, in terms of schedule, and in terms of cost overruns. And so here's a notional architecture of a human machine interface. And so the human machine interface basically deals with the physical aspects of it, which is, you got the user, and then here's the user interface. So the user interface could be a speech recognition, microphone input. It could be a touch screen. It could be a bunch of switch closure switches. Um, it could be just about anything. And then there's the machine interface. This interface can be physical lines, like, for example, RS-232 or Ethernet connection to a robotic system, for example. And then this portion right here is the behavior, which is mostly in software. To some extent, it can be in hardware. But you got the display presentation. How are you displaying the information to the user? The control interface. How are you controlling the display of information? The dialogue. Dialogue very critical, because the dialogue basically navigates the user through the application to understand what he or she needs to do next or afterwards, or did they make a mistake, and things like that sort. So the dialogue is a critical part of the behavior, usually coded in software. And then the application interface that basically is talking to the machine. So the machine provides status and also accepts commands. And then that information is fed back through the dialogue and the control interface back to the user. In addition, we also have to have cascades to help, depending on the complexity of the system, like, for example, electronic procedures or autonomous systems. One of the cautions about autonomous systems is that you have to design the autonomous system to provide status to the user, knowing where they are in the application. If the autonomous system is doing the application, that there's a way to basically intervene. In other words, take over the commanding of the system. And here's an example: Tesla. Tesla has, Tesla is using the autonomous vehicles, and I don't know if you've heard about, we've had some accidents in the United States that kill people because the autonomous system failed to understand the environment, and it crashed into in one case it was a truck, in another case it went into a swimming pool. So you got to have some kind of way of using cascades, but making sure those cascades do not make the workload harder on the astronaut. The goal is to make the function of the technology obvious to the user while improving productivity and reducing error. The machine to help the user accomplish their task. It's not, the machines it's not the machines that were built that the user has to understand how to use in order to accomplish the task. So it's the other way around. All right. So principles of human rating systems. These are three fundamental principles of NASA engineering processes associated with human design in safety critical applications. One is to make sure the total system can safely conduct required missions. I can tell you that safety is number one at NASA. It's not so much the mission. Obviously, we want to be successful in the mission, but the safety of the crew is number one. Machine interaction design features and capabilities enhances the overall safety and mission success. We want to make sure that this interaction, this machine design, does not make things complicated for the user. We're trying to make it easier for the user. That's the important thing. And then the human machine interface features and capabilities enable safe recovery of the crew from hazardous situations, tolerate inadvertent operations by detection and correction of human error. This is the feedback. Okay. Oh, wait a minute. No, you cannot do it. You cannot press this button. You got to press this button first, and then this button. Or arming the system. Are you sure you want to activate this thruster? If so, then go ahead and press execute. So there's a arm and fire. It takes two stages in order to activate a critical function. Crew workload and usability. There's testing that's done to assess how much workload and usability a human interface is to the user. Operations of controls. Humans in space are not sometimes suited in a spacesuit, and so they have glove operations using this heavy duty, massive glove versus ungloved. That glove can pose a lot of problems because the end of a finger is pretty big. In fact, you got to design separation of command of control buttons roughly about an inch apart, so that way that glove can go easily and punch just one button and not two buttons. All right, so we got to design for the human, designing the human interface. There's the physical aspects of it. You got physical machines. You got computers, you got switches, you got control cable, you got cabling, you got all kinds of things like that. So you got to design for the environment: temperature, vibration, electromagnetic compatibility, humidity, shock, radiation. These are things that electrical engineers, software engineers understand quite well. In addition to that, we have to design above and beyond what we think is good enough. We got to rate system components. What does rating mean? It means that you operate components at a lower percentage of their capabilities. For example, if you got a transistor that can operate with a maximum current of 60 milliamps, you don't want to operate it at 60 milliamps. You're stressing it. You want to operate it at 30 milliamps. You're only operating at 50%. Failure modes and effects analysis is basically what can go wrong and how do we mitigate that. So that's a big thing in doing analysis. I can tell you that these two were not taught to me in school. I had to learn that when I came to work in NASA. And then the human-machine interface, vision. How far are you away from a display? What are the colors? The glare. Okay, the glare is if the sun is shining on the display, can you still see the display? Hearing, noise frequencies, intensity output, announcing tones and noise. If you're announcing a tone that cannot be heard and it's an emergency tone, your astronaut is in trouble. Touch, tactile. What is the feedback? For example, for electromechanical switches, it's pretty simple. You flip a switch and you can hear it click. For touch screens, you don't hear it click. You got to think of different ways of providing feedback. Like for example, a blooming effect. When you touch it on the screen, it kind of blooms to indicate the system recognized the touch. Design considerations. We continue on with visual seeing the displays. Again, color, font size. How big are the letters, brightness, colors, caution and messages. You don't use red to indicate everything's okay. Red means there's something bad going on. Green means everything's okay. Yellow or amber, caution. So you got to be careful about color schemes. Auditorial, again, you got to deal with environmental noise, caution, warning tones, the intensity of the tones versus the background. You might have reverb and echo effects because of the spacecraft. You got to deal with that. Tactile feedback is critical, as I mentioned. mechanical versus touch. There's safety considerations for each one. Hardware switches for time critical functions. You probably want to look at using hardware switches for time critical things like um, uh, maybe activating a thruster rather than doing touch, because if the touch doesn't register at a specific time, you might be in trouble. Multi-contact design. Multi-contact design is basically a switch that's got three contacts, and the software and the hardware, instead of just recognizing one contact that's either on or off, it looks at three contacts to verify that indeed this switch was depressed. Switch guards to protect against inadvertent switch closures and switch transitioning to another state. I can tell you that state transition, for those of you double E's that know state machine design, uh, it's a big issue with hardware interfaces, and things like transitioning from an auto to an on state can cause problems if your software in your state machine doesn't factor into the design of, let's say, for example, not being active during a transition of one state to another, but then becomes active once it goes into a new state. So there's a lot of schemes about that, but state transition or state machines is a biggie in terms of human machine interface. Command activation, must work functions. These are functions that have to work. Like, for example, firing the thrusters to land on the moon. That's a must work function. Firing the pyros for parachute deployment if they're coming back to Earth. That's a must work function. And then putting functions into groups. You want to put all your environmental life support systems in one section, your power systems in another, your let's say, for example, your navigation systems on another. So that way you've grouped your functions in your systems according to what they're supposed to be doing. Status lights. this this is this was a problem in many shuttle flights. Was is the light the status of the switch or the status of the system? You have to be specific as to why that light came on. What's the meaning of that light? And then design optimization. I'm just kind of briefly go. This is a kind of a repeated systems engineering process, requirements, specifications, implementation. You're doing hazard analysis along the way, trying to get rid of any hazards that have been identified. This is part of the human systems integration process or human-centered design. You're constantly iterating in terms of factoring the human element into the design of the system. And as part of the human-centered design, you're doing basically three things are going on. You're designing the hardware system to match to the human, and then you're also doing a test design to match the test of the human. Some tests are not suitable for the human. Some are actually more suitable for a machine, and that's why during early in the systems engineering process, there's something called allocation of requirements. So the allocation is basically, am I going to have this done by a human or am I going to have this done by a machine? And then the test design to the hardware design is to match the design to the test. All this is going on as part of your human in the loop testing. You're looking at usability, things like error rates. How many errors is this person doing using, rather, how many errors is this person exhibiting using the system? The tasks, the steps for success, efficiency, test completion time, deviation from the best path, and then user satisfaction. So there's workload, there's usability, but you're also verifying these requirements. Verification early on during the development of a system, but then verification later when you're verifying the final system design. This all goes into the human-centered design process. Again, lots of iteration, but you got to do that, especially if you're dealing with humans and safety of the humans in deep space missions. And so I'll wrap up here is, we have to understand human computer interface or interface, human machine interface design for space. It requires many aspects of it. It's not just the human factors element, but also the environment, designing for that environment, safety, which is utmost important, obviously electrical and as well as software design. A well-rounded engineer should understand systems engineering and human systems design. I can tell you that from personal experience. Again, not taught in undergraduate school for me. It was just teaching you about hardware and software. And then design of a human machine interface is a quite an iterative process design. But you got to do that, and especially for safety critical missions, because you're trying to get out, weed out issues associated with the system that can affect the mission. All right, so that concludes my presentation, and I think we got maybe about 25 minutes to answer questions if I can.
Okay, thank you very much for this, Mr. George. Okay, now let's open up for the Q&A session. Let's see. So there's one question. What are the main bottlenecks in deep space missions? So let's say, is it to develop the propulsion system so we can lift up more weight, or is it the human condition, or is it the communication?
It's all of them. For a deep space mission, everything has to be considered. You can't omit any of them. The deep space so one factors another. Like for example, because of the time delay, you have to think about okay, so a time delay for a specific event. Let's say, for example, fire in the habitat or fire in the crew cabin. All right. Well, you cannot send a message to mission control and wait 20 minutes later to get a response. You got to take the action now. So your design has to factor that delay in there. So everything in a mission has an importance in deep space missions.
Okay, great. So another question is now you mentioned that especially when it comes to electronics and software, there should be redundancies. So I've read that there's called triple module redundancies you implement on programming. So when there's a bit flip effect, which is caused by cosmic rays or other radiation doses. So do we really still need redundancy schemes if our electronics are radiation tolerant? If now there are new chips that are coming out from, for example, such as Xilinx, they are rolling out new microchips, new IC packages which are radiation tolerant. So do we still need software level redundancy if our hardware level is radiation tolerant?
Radiation is a big thing, and so there's different ways of dealing with radiation. One is to buy radiation hardened components, and they're very expensive. For example, a field programmable gate array commercial version may run you maybe $100. A radiation hardened FPGA will run you about $75,000. But it's meant to survive in the deep space radiation, and so it's just not single event upsets that's a problem. Single event latch ups, and then total ionizing dose radiation, which is a big event, is a biggie. And so when I was talking about artificial intelligence, the computing power associated with artificial intelligence is basically what you hear right now in the news in terms of, let's say, the Google search engine, NVIDIA processors that are meant for artificial intelligence. But these are high performing devices, and they consume quite a bit of power too as well. But these don't do very well in the deep space environment. And so if we are going to use, let's say, commercial type products for deep space environment, we have to find ways of dealing with radiation effects. And so one way of doing it is to basically do radiation tolerant design. So how do you do that? You do that with different methods, whether it's error correcting code, or let's say sometimes another one is scrubbing memory, and then sometimes another one is voting. So you have voting logic, which is quite common in some of the radiation tolerant processors, is that you vote on the data. However, for commercial products, they can do that up to a certain point, but total ionizing dose is eventually will take its toll on the life of the component. And what happens is that the signals start to slow down, it starts to misbehave. And so we're going to have to figure out ways of dealing with that without sending a whole bunch of spares into a deep space mission. Because every time you send spares, that means you have weight, and more weight means it takes more launch power, and it gets more expensive. And so it's a major trade. I can tell you right now, I'm working on some research in terms of graphics processing units for deep space missions. It's a major challenge. We took many graphics processing units, commercial processing units, to high energy proton testing, and they all failed miserably. So we got a problem.
So these are from NVIDIA and ATI, these GPUs.
Yeah, NVIDIA, and they have tested some parts of NVIDIA, and some parts do well in proton, but not in heavy ion. And a lot of the deep space radiation is heavy ion, and those are tough to deal with.
So, Mr. Salazar, you work on quite a deal on implementing voice control systems for spacecrafts. Can you give me an application? How could that be beneficial? Does voice control methods hold true in space conditions?
Sure. So we're looking at voice control right now, revisiting it again, because voice control basically provides an extra pair of hands to an astronaut. So you can control a machine while you're doing switches, using switches here. You can control another machine by voice control. Another application that could potentially be used in deep space missions is when the crew has medical issues, that they are what we call incapacitated. In other words, the only ability they have is just to speak. They're weak, or something's happened to them, and they can't reach for a panel. They can't do switch closures, and so the only thing they can do is send commands by voice. And so that's something we're looking at here again. Speech recognition, it's a major challenge. When I did the experiments on shuttle, the challenge was trying to make the command structure very minimal so that they don't have to remember a lot. And of course, we had a little display at that time that provided an indication of where they were, but sometimes they would just forget. And so it's a major challenge in designing speech recognition systems. It's not so simple. I can tell you early on, people were using speech recognition quite a bit, and there was a lot of failures because they failed to understand what happens to the voice of a human in space applications. They failed to understand what happens to speech in a reverb environment, acoustically challenging environment. I can tell you that way back when, a lot of the speech recognition companies would advertise 99% accuracy, but they would not tell you that that was in a very quiet, controlled laboratory, not in the real world. And so when we would test these systems in our application, they did not work well at all. So speech recognition is a viable option, and we're looking at possibilities of using that, but the caution has to be that it has to be implemented correctly, and it takes experience. You just cannot just say, "Oh, I'm just going to use speech recognition and not worry about the human element," because again, if the human is not feeling well that day, they're not going to speak the way they did when they were actually using the system when it worked quite well for them. Or it gets really noisy inside the spacecraft, and then all of a sudden they start shouting to the machine. Well, your shouting is actually saturates the microphone input, and it distorts your audio, which means it's going to have trouble understanding you. That's been a big problem actually in automobiles in the United States. I went to a conference where a this particular automobile manufacturer said that the two top issues for automobiles was speech control and Wi-Fi. I'm sorry, not Wi-Fi, Bluetooth. Bluetooth. Yeah.
So speaking from your human-machine interface experience, so if we know another method of the human-machine interface is the touch. So if you want to control a craft, so in the beginning of the space exploration, we can see a lot of tactile buttons on the cockpit. But if we look into the new cockpits, especially the one was designed by SpaceX, the Crew Dragon capsule, it is mainly a touch screen. So it does look futuristic, but is it really robust? I mean, if you broke your screen, you don't get to access your commands. So which is better, that all school tactile buttons or the touch screen?
All right, so let me tell you about SpaceX touchscreen. That touchscreen is used for non-critical commanding. The only time they use it for critical commanding, the only time they use it is when they're going to use manual piloting, when they pilot the vehicle manually. And so what comes up is a touchscreen with up, down, left, right, so to speak, translational and rotational. But the only way to activate that, and this is something that's not advertised, but you'll see it on on a lot of pictures, right below those three displays. Right below there are 30. I think there's 33 manual switches, buttons that are used for critical commanding. So some of the buttons is like, for example, powering on and off a particular display. Parachute deployment, there's a button for that. There's a button for rebooting the flight computers. Okay, so it's a manual button. It's not a touchscreen. Let's see, and then there's other buttons that are used for critical commanding of the spacecraft. But again, the separation between non-critical commanding and critical commanding is evident by using touchscreen for non-critical stuff, and for critical stuff, you still rely on mechanical or physical buttons.
Great. So the next question I would like to ask is that with time, the orbital time which is left for the International Space Station is decaying. So after some time, NASA would have to abandon the International Space Station. So what are the plans after this? I've heard about the Deep Space Gateway, which would be a space station that would orbit around the moon.
Yeah, I mean, we're working right now on Gateway, and the Gateway is let's call it the Moon space station. So it's going to be smaller than the space station that we have right now orbiting the Earth. It's intended to provide a let's call it a orbiting platform for dealing with sustainment, or rather for sustaining astronauts for a long period of time on the moon. And so basically they'll have the human lander system. That's something I've been working on. which takes them to the ground or on the surface of the moon, and then launches them back to the gateway. But the orbiting space station right now, I think they've extended its life to 2029. There's going to be a point where they're going to have to retire the space station because it gets too expensive. It's breaking down. Maintenance is a big thing. Astronauts spend probably 70% of their time maintaining station. The other 30% is actually doing scientific research. And this goes back to human systems integration, is planning for the human element in a spacecraft design. Same thing happened with space shuttle. They failed to consider the human element in design. They would work 3 shifts for months in order to turn the space shuttle around for the next launch, just simply because the way things were designed. I can tell you that I remember one time I was working on a flight project, and they made an announcement that everybody had to leave except for the people that were working on the orbiter maneuvering system of the shuttle. And so a whole bunch of people were exiting the building, and just a very few people in there, and we had to just kind of like wait around until they finished operation. So very inefficient, but it's the way it was designed. And I can tell you that there's one particular spacecraft that had an issue where the power supply was not easy to get to. And so they had to basically take apart quite a bit of the spacecraft to get to the power supply. So, you have to think in terms of maintenance. You got to think in terms of operations. You got to think about, the human. There's too many stories to tell you about inefficiency in human design, but sometimes designers tend to design something that will never break, that they never have to maintain. And so, there's too many examples. I can give you one example where one person designed a system that during thermal testing, they needed to look at some certain signals on the circuit board. But he did not design a way to take those signals out of that circuit board so they could monitor it. So they had to what we call rig the circuit board with all kinds of wires and stuff in order to get the signals out. Very, very bad. It was very bad. And so things like that happen, that you learn either because of mistakes, or you learn from other people that have experienced that.
Great. So moving on. So around June 2020, you co-authored a paper titled as Technology Readiness Level as the Foundation of Human Readiness Level. So with that, I think you would be the most suitable person to ask questions that goes to the realm of science fiction. So in your experience, what is the technology readiness level for a SSTO, a single stage to orbit craft?
Okay, so you want, can you repeat the question, please?
So what is the technology readiness level for a SSTO, a single stage to orbit craft?
So the paper you're referring to, the foundation of human readiness level with TRL, or technology readiness level. So right now NASA uses technology readiness level as a let's call it a management tool that everybody understands. When somebody says this technology is at TRL level 3. So it has a specific definition, which basically says this thing is being developed. It's still under development. It's not ready for flight. And then it goes from 1 to 9. 1 is basically, number 1 is just basic research, all theoretical stuff. And then 2 and 3 is kind of like, well, I'm doing a little bit of lab work and, kind of put together a little system here that I'm experimenting with. And then 4, 5, and 6 is basically you're building something that's a little bit more refined, a little bit better. And when you get ready to go to preliminary design review, at least at NASA, your system has to be at tier level 6. What does that mean? Tier level 6 basically means you build a functioning unit that's operating, that does what it's supposed to be doing, and it's been tested to different environments that suggests that this thing can work in the application. So at PDR, you say, okay, I'm at tier level 6, and they say, okay, good. And then you got to take it further. You got to take it to tier level 8 by the time you get ready to fly. When you fly and the system operated properly, now it becomes a TR level 9. In other words, it's flight proven. So contrast that with the human readiness level. There's nothing like that for human readiness level. And that was the argument in the paper, is that if you have something for human readiness level, you can now show how mature your human computer interface is in readiness for a flight. So as you start maturing the readiness of the human with the technology, as it matures, it tells the management, yeah, this stuff is maturing at a good rate. But if you go to preliminary design review and you say, my technology, my human machine interface is at tier level 3, but my human readiness level is at 6. Okay, there's a mismatch here, or vice versa. I'm at tier level 7 in technology, but my human readiness is at tier level 3. Well, that tells me that, yeah, you matured your technology, but the human is having trouble understanding your system. Okay, and so it's flags, basically management flags to indicate how well the system is being matured as technology is maturing as well. So the argument here, and there's going to be a in the fall of this year, hopefully, ANSI is going to publish the standard on human readiness level. So hopefully this will be broadcast out to industry, and then NASA will embrace it. We embrace it to some extent, but not fully. But I think it's a step right now. But eventually we'll have more of the human readiness level as well as technology readiness level. It took many years to get acceptance on technology readiness level. Sometimes the government operates very slowly.
It's the same here. It doesn't make any difference. So have you read the Space Odyssey by Sir Arthur C. Clarke, the 2010 Space Odyssey?
What paper is that?
2010 Space Odyssey by Arthur C. Clarke, a science fiction story.
Oh, no, I haven't actually.
So anyways, the question is like now the icy moon of Europa. There are theories that it's the crust, it's the ice, but beyond the crust you have an ocean. So how long will it take for NASA to send a probe, and we can drill the crust and put a probe, and we might see the first alien marine life at Europa?
Okay. So the Europa mission, yeah. I know there's been. I kind of. The last episode was that they were planning that mission, and I think within the next 10 years is where they want to send a probe, basically a little mini submarine, if you will, that goes into water and does probing underwater. I mean, there's so much to learn about about the universe and the um, and all, the possibilities of life on other planets. And of course, right now we're focused on Mars, because of the nature of how close Mars is to the Earth. And Mars at one time was somewhat like Earth, and it died off. It lost its atmosphere and all that. And why that happened? That's one of the things we're trying to understand is um, are we going that way? And of course, if you look at Venus, Earth, and Mars, we're in what they call the Goldilocks zone of life habitat relative to the sun. But it's it's kind of a long discussion. But Venus at one time may have been a little bit like Earth, and it just died very quickly because of the greenhouse effects, and obviously it had major climate change without any humans there. Mars, same thing. They had, and its climate has changed over the centuries and whatever, and so it's losing it's lost its atmosphere. It once had rivers, and why did those rivers dry up? I can tell you from astrophysicists that I know, one day Earth is going to be that way. The Earth, as the sun gets older and older, is going to start losing its ability to produce energy, and I forget the term that they use, but the sun eventually is going to die, and when it does, it's going to grow, and Earth's going to get very hot, and it's going to melt away the oceans and all that stuff. Of course, we won't be around, but it's just inevitable that it's the nature of how solar systems, you know, uh, just like humans, they're born, they live, and they pass away.
So, Mr. Salazar, so this final question, I mean, I think you have been barraged with this question for a long time. I watched one of your previous sessions with some of the Indian students from YouTube. So this was the final question as well, and this will be the final question in this session as also. So the reason is that most of the students has asked this. So I can partially answer this. The question is, how can one who is not born on a soil on America, who's not an American, can work for NASA? So the partial answer that I will be given is that you can't work for NASA because you are not an American citizen. But what I would like to ask from you, Mr. Salazar, is what would you advice would be for someone who's still grasping, still pushing for that dream of working for NASA, even though they are not American?
All right. Yeah, I'm asked that question quite a bit, and I can tell you that it's a long road. And but let me just share with you a student from India, female student that approached me about 5, 6 years ago, asking me that question. And so I kind of looked around and I found out that yeah, there is an opportunity, but it's a long road. So um, I told her, I said, her Basura is her first name, and I told her, graduate get a bachelor's in India, come to the United States and get accepted to a master's program in engineering. So NASA hires a lot of engineers. We do hire some scientists, but more so engineers. And so I told her major in software engineering and especially artificial intelligence and machine learning. So she got accepted to the University of Syracuse University in New York in the United States. She got her master's, and then she's now pursuing a PhD in California, and at a university that has people that work at JPL, Jet Propulsion Laboratory in Pasadena, California. And I told her to hook up with a professor that works with NASA and study under him or her. And and that's what she's looking at right now. So she has come from, being a high school student in India all the way to now getting close to finding a professor that supports NASA. So once she does that, then she's also looking for citizenship, and it's a mixed issue for some people. I've talked to some students, one in particular from Africa, that they don't want to give their citizenship up, and they, for whatever reason they want to stay in Africa and not become a U.S. citizen. But it's part of the sacrifice, if you will, if you want to come work for NASA in the United States. But at the same time, I'm learning that ISRO is pursuing a human spaceflight program, and so maybe they don't have to come to the United States to get involved with human spaceflight. India may have opportunities that will be easier for students to do. But if you want to come and work in the United States, especially if you want to be a civil servant like I am, I'm a U.S. government employee with NASA, and you have to be a U.S. citizen. Some companies, contractors that support NASA, like for example Lockheed Martin, Boeing, require U.S. citizenships. My understanding, I have not verified this, like companies like private companies like SpaceX or Blue Origin and others like that may allow you to work with a green card. So there's different options, and I have to just say to do a lot of research. Do the research. To figure out what's the best opportunity. But there may be opportunities there in India in the future with ISRO up and coming with human spaceflight, and they've already accomplished quite a bit. They got I think they got a probe orbiting Mars. So it's India's. I think India is going to be one of the few that are going to be doing human spaceflight, along with the Chinese and obviously Russia too as well. I hope that helped.
Thank you for that answer, Mr. Salazar. That question was a bit personal for me. I also grew up with that ambition once. So with that, we can wrap up the Q&A session. Sharoni, it's over to you now.
All right.
Thank you, Mr. Ravindu. I will now take this time to convey my sincere appreciation and thanks to Mr. George Salazar for humbly accepting our invitation despite his busy schedules and for sharing with us invaluable knowledge on the topic beyond the terrestrial. We appreciate having this mysterious area clarified to our audience. Please accept this digital token of appreciation. This is for your contribution towards making this event a memorable one.
Thank you.
Next, I would like to thank our moderator, Mr. Ravindu, for your excellent job on moderating today's panel discussion. You pulled it off impressively and kept us all at the height of our attention. Please accept our token of appreciation for your contribution.
Thank you. Thank you for this.